In this lesson, we're going to talk about continuity and one-sided limits. For the one-sided limits, we say that the limit as x approaches c from the left is denoted by x approaches c with a little negative sign right here. And so this is how we denote approaching c from the left. And we have the same thing if we approach c from the right. We just have a little plus sign right here. Okay, so this is really about notation. Now the existence of the general limit, that is, if we're just talking about, hey, x is approaching c, we don't specify coming from one side or the other, that general limit exists if and only if the limit from the left is equal to the limit from the right. And now I've said that in another video, in a different way, but it's saying that you've got to come towards the same number from both sides in order for that limit to exist. So let's look at an example. We want to evaluate the limit as x approaches 5 from the left of this function right here, the square root of x squared minus 25 over 5. Now, maybe it'd be helpful if we start off by thinking about, well, what if we were doing this from the right? If we were doing this from the right, we would have numbers that are a little bit more than 5. And if we stick numbers a little bit more than 5 in here, then we end up with something that's a little bit more than 25 when we square that. And whatever that is, minus 25 is some positive number, and divide that by whatever the x is, and we get a limit there. But we're coming from the left in this case. And so if we're coming from the left, we're talking about numbers that are a little bit less than 5. Think about the numbers like, 4.5 or 4.9, 4.99, those kind of numbers. And if we stick those into here, we end up with something that's a little bit less than 25 when we square that thing. Take something that's less than 25 and subtract 25 from it, you end up with a negative number underneath the square root. And so that's something that we can't have. In this case, this limit does not exist. And if we take a look at the graph over here, then we can see kind of what's going on in this case. If we were approaching 5 from the right, there wouldn't be any problems because this thing is coming here, the y value is getting closer and closer, looks like it's getting closer to 0. But coming from the left, there is no graph there. There's nothing for us to look at. And so the only way that the limit exists is if both things are coming towards the same number. Well, there isn't even a limit coming from the left over here. And so they can't be coming towards the same number. That's why this limit doesn't exist. That's why, in this case, the general limit wouldn't exist, nor does the left-sided limit exist. All right, let's look at another example. We want to evaluate the limit as x approaches 1 coming from the right of f of x. And here f of x is defined this way here. F of x is equal to x plus 2 if x is less than or equal to 1, and it's 2 minus x if x is greater than 1. So if we're approaching 1 coming from the right, then we're talking about numbers that are a little bit more than 1, which means that we would be looking down here to see how f of x is defined. So we're talking about numbers like 1.1, 1.01, those types of numbers. And so it looks like the closer we get to 1 coming from the right, the closer this number right here is going to be to 2 minus 1, which is going to be 1. It looks like we have a limit of 1 in this case. And we can see that happening down here. In this case, this is the graph of it. In this case, if we were approaching coming from the right, coming this way, we can see that this y value right here is getting closer and closer and closer to 1. If we were approaching coming from the left, well, we see that we could also do that limit. We could find out what that limit is. It looks like this is approaching, 4 maybe. And so we could evaluate the limit coming from the left. Note that this is a case where the general limit would not exist, though, because in order for the general limit to exist, what's coming from the left and what's coming from the right, they've got to be coming towards the same number. So we could do the one-sided limits for this function, but we aren't able to find the general limit as x approaches 1 for this one. Let's talk about continuity. Now, you may remember from algebra or pre-calculus, when you talked about continuity, generally the way it's described there is that if you got some kind of a graph, and if you can draw the graph without lifting up your writing instrument, then it's continuous. Well, in calculus, we have a little bit of a different way of approaching that. We have a definition here that says a function is continuous at a certain point, at x equals c, if and only if the limit x approaches c of f of x is equal to f of c. Now, let me point out that there's actually kind of three things that are going on here. I'm going to just write these in. Three things that are happening here. One is we're saying that the limit as x approaches c of f of x, that exists. Okay, so that's one thing that we're saying. That exists. The other thing we're saying here is that f of c is a number. It's defined. So f of c is defined. In other words, another way of saying that is that c is a number that's in the domain of f of x. And then the third thing that's saying is that these two things are equal to each other. The limit as x approaches c of f of x is equal to f of c. And maybe an even simpler way of saying this is just by saying, hey, we can do this limit using simple substitution. Remember, that's our first approach when we're trying to evaluate a limit. We just try to say, hey, can I just substitute this in? If I can do this limit by simple substitution, then the function is continuous at that number. Okay, so we're going to look at some examples here, and really the thing we're trying to figure out is this function continuous at the given value? So here we have f of x equals 3x squared minus 5x plus 1. I want to know, is this continuous at x equals 1? Well, the question is, if I'm trying to find the limit as x approaches 1 of this function right here, does that limit exist? And does that limit equal f of 1? Well, let's go ahead and evaluate. What is f of 1? That means I would stick a 1 in place of x up here. That'd be 3 minus 5 plus 1. Looks like that would be negative 1. How would I find this limit? Well, the first thing I would do is I would try simple substitution. And it looks like I wouldn't have any problems. I don't get any negatives under a square root or zeros in denominator. I would just put this number in. And so that ends up giving me negative 1. And because these two things are equal, we can say that this function is continuous at x equals 1. And what you'll find is that with polynomial functions like this, it's going to be continuous everywhere. Polynomial functions are kind of those roller coaster functions that just have curves and valleys and hills and things like that. Those are continuous everywhere. Well, what about this one? We want to find out whether this function is continuous at x equals 0. Well, the first thing we want to know is, does the limit as x approaches 0 of f of x, does that exist? Okay, so if that exists, we know that the limit coming from the left must equal the limit coming from the right. Let's look at the limit coming from the left. The limit coming from the left, remember our notation here, we have a little negative sign. The limit coming from the left, well, if we are approaching coming from the left, that means that we're looking at numbers a little bit less than 0. That means I would look up here, right? This is how f of x is defined if x is less than 0. And so if x gets closer and closer and closer to 0, x squared is going to get closer and closer to 0. Looks like the limit coming from the left equals 0. What about the limit coming from the right? Okay, the limit coming from the right, if we're approaching 0 from the right, we're talking about numbers a little bit more than 0. And this is how f of x is defined if x is more than 0. And so if x gets closer and closer and closer to 0, this quantity right here gets closer and closer and closer to negative 3. And what we see here is that these two things are not equal. The limit coming from the left is not equal to the limit coming from the right, which means that the general limit does not exist. And I can stop there because I can see this limit doesn't exist. So there's no way that those three conditions I just outlined are satisfied. There's no way that this is equal to f of 0 because this limit doesn't exist. And so what that means is that it is not continuous. And you can actually go a little bit further and say, well, okay, I know it's not continuous because if we're approaching 0 coming from the left, this heads towards 0. Approaching 0 coming from the right, this heads towards -3. When I look at this graph, I don't know exactly what it looks like, but I know that at 0, this thing's coming up here and heading towards 0. But over here, coming from the right, it's heading towards -3. I've got a jump in the graph right there. Okay, what about this one? We want to decide if f of x is continuous at the given value. And here we've got this function, and this is at x equals 3. So I want to know, first of all, does the limit exist? X approaches 3 of this function, x squared minus 2x minus 3 over x minus 3. I want to know, does this limit exist? Well, if I try to stick 3 in there, if I try to do this using simple substitution, what I find is that I get a 0 in the denominator. And a 0 in the denominator means, okay, I got to try something different. It doesn't mean the limit doesn't exist. That's something that's easy to say. That's something that's a trap because a lot of people make that mistake. It doesn't mean this limit doesn't exist. What it means is that I can't do it just using simple substitution. But we know that limits are algebraic. And so maybe I could try some algebra here and see if I can evaluate it that way. And it turns out that if I factor the numerator up here, and then cancel out what's causing the problem, then I can evaluate this limit. The limit as x approaches 3, I'm just left with an x plus 1 right here. Looks like this is equal to 4. Okay, so the limit exists. Okay, so I want to know, does that limit equal f of 3? Well, f of 3 would just be taking 3 and sticking it into this function up here. And we see that if I stick this 3 into this function up here, I get that 0 in the denominator. This is not defined because the number 3 is not in the domain for this function. So this is not defined. And because of that, what I see here is that, again, we find that we have a function that is not continuous at the given point. Okay, now if we were to go in here and look at this graph, what we would see is that, you know, this function is defined for everything except for that one value right here at x equals 3. That one value is the one where it's not defined. In fact, the graph would look like x plus 1. It would just be a line, but at x equals 3, there'd be a hole in the graph. The graph would look something like this right here. So it's defined, and we can see why that limit up here existed. You know, if we're approaching 3 coming from the left or from the right, they're both approaching the same number. So the limit existed. It's just at 3 itself that there's a hole in the graph. So in this case, what we've got is what's called a removable discontinuity. If the limit as x approaches c of f of x equals some number L, but f of c is not equal to L. All right, so that one place right there, when I stick c into that function, I don't get that limit, then the point at x equals c is said to be a removable discontinuity. And what we can do is we can remove that discontinuity if we just sort of redefine the function. If I went in here and wrote, okay, f of x is equal to, and I'm writing it down exactly the way it was up here before. Okay, so that's the function. And that's what the function is as long as x is not equal to 3. But if I say, okay, well, what happens if x does equal 3? Well, that would just be saying, well, you know, what is this number right here? Okay, that would be 4. So if x equals 3, I'm going to let f of x equal 4. Essentially what I'm doing in that case is I'm just going over here and I'm just sort of filling in that little dot right there. I'm removing that discontinuity. And remember where the 4 came from is because that was what the limit was right up here. And I will note that actually my graph is a little bit wrong here. It looks like this is not the graph of this right here. The graph here would look a little bit more like this. But you get the point, I think. The hole would be here. Anyway, you get the point. I hope this has been helpful.